So let me conclude this lecture by showing that if we were to solve the problem in the Heisenberg picture, we would also get the oscillatory behavior. So in the Heisenberg picture, um, we are interested in x of h, which is the position operator in the Heisenberg picture, and that is going to be a function of t, and then this is going to be given by the unitary operator u dagger of t acting on x in the Schrodinger picture, which is identified to Heisenberg picture x at time 0 and then u of t. So we are treating this x as an operator, so we are not going to commute it. We are not thinking of x as a number. So what is u dagger? U is, so okay, so to use this, we use the BCH formula. And according to the BCH formula, this is going to be equal to an infinite sum and then minus I h bar divided by, this is minus I t by h bar to the power n divided by factorial of n, and then the commutator of h, nested commutator of h, n times with x and at time 0, and then we just stop the nested commutator. So this is what the BCH formula tells us. So now we have to evaluate all these terms. So to do this, recall that if I look at the commutator of the Hamiltonian with x, what do we get? So the Hamiltonian has two terms. One is p squared, another term is x squared. Of course, there are coefficients, which I'm going to ignore. Well, not ignore, but I'm representing by a and b. And x squared will commute with x. So the commutator of h with x will be given by 1 over 2m, the commutator of p squared with x. And this is easily using the identity of writing the product of operators in commutators in terms of commutators of individual operators. We can, and also using the fundamental commutation relationship, this is easily shown to be I h bar m times p. And similarly, if I evaluate the commutator of h with p, this is going to give me half m omega squared, commutator of x squared with p, and that will be given by I h bar m omega squared x. So after this, we can say what is the commutator of h with the commutator of h of x. So we can use this relationship here, and what will we get? We will get minus I h bar m, and then we'll get the commutator of h and p. So here we will use this relationship, and therefore we get I h bar, we get h bar squared omega squared of x, right? Because there's a factor of m here and there's a factor of m here, so those two m's will cancel out, and the factor of I and minus I will give me a plus sign here. So similarly, we can now do evaluated the three nested commutators, and so to do this we can use this guy, and then what we get is h squared omega, and then we have h and x, and therefore we are going to get minus I h cubed omega squared P over M. So similarly, if we now do 4 commutators, nested commutators, then you can work out this is going to be h to the power 4, h bar to the power 4, omega to the power 4 times x. And then we can do 5 nested commutators. I promise I'll stop after this one. And this will be minus I h to the power 5 omega to the power 4 p over m. So there's a pattern emerging. And the pattern is that the first commutator of x with h gives me p. But the next one gives me x. And the next one gives me p again. And the next one gives me x. And the next one gives me p. And therefore, we can rearrange our x of h of t in terms of 2 series. The first series is the series only with x, so we can factor out x of h, and then we have in that series 1 plus minus it divided by h bar squared by factorial 2. This was already in the definition of the BCH formula. And then we have figured out it's going to be multiplied by h squared omega squared. So this is coming from the term with 2 nested commutators. And then the next term in the even series will be minus it over h bar to the power 4 divided by factorial of 4 h to the power 4 omega to the power 4 dot dot dot. And this is going to come from the nested 4 nested commutator term. So this is the even series. The odd series is the one which will have p, and we can factor out minus p over m, and this is the Heisenberg operator at time 0. This is also at time 0, and the odd series is going to start with I t over h bar times minus I h, and then we will have plus minus it h bar cubed 1 over factorial of 3 times minus I h cubed omega squared, and then we will have plus minus it h bar factorial of 5 1 over factorial of 5 minus I h bar 5 omega to the power 4. Now if I simplify these 2 series and use the fact that the Maclaurin series expansion of cosine is given by 1 minus theta squared by factorial of 2 plus theta to the power 4 by factorial of 4 minus dot dot, and the Maclaurin series of sine of theta is given by say theta minus theta cubed by factorial 3 plus theta to the power 5 by factorial 5. Well, there's a minus sign after that, blah blah, and then we can use this to write x of h as a function of t, and this turns out to be x of h at time 0 times cosine of omega t plus p of h of 0 by m omega sine of omega t. And so we leave it as an exercise to show that this thing, the expectation value of x and its time dependence is given by this thing, of course, at time 0 cosine of omega t plus time 0, and I'm going to leave it as an exercise to show that this thing is the same as the time-dependent expression that we got in the previous section.